Chris Clements again with another podcast. This one will be on reaction types. We've hopefully before this gone over balancing equations. So I'm going to go over 5 types of reactions, but there are subtypes in them. So let's go ahead and get started with the first type of reactions called composition. There are other names for this, but I will stick with one name for each of these. Composition. Composition, as you can see, has a generic, as I give you on each of these slides, a generic form. A plus X means 2 substances come together to make AX. It's not necessarily 2 elements. It's not necessarily 2 compounds making a third compound. It can be just a medley of things. The key thing is you get one product out of the reaction. So what I'm going to do for each of these, as I will do for this one, is give you an example reaction. What your practice sheets will have is exactly what I'm about to give you, just in word form what the reactants are. You must predict the products. You must write a balanced equation once you have written your formulas for reactants and products. So here we go. Your first type of reaction is composition. We're going to combine 2 substances. And the substances of choice are barium metal reacts with nitrogen gas. I'm going to go through each of these that I give you so that you have an idea of what to expect. So what you need to do is write your formulas for Ba, barium, and N2, nitrogen gas, since it's a diatomic molecule, that will react to form one compound. They will form barium nitride. Barium nitride, you need to think about the charge of barium and the charge of nitride. So your formula for your product is Ba3, N2. You then need to analyze it and determine if it is a balanced equation. Indeed, it is not. You do not have a balanced number of bariums on each side, so fix your bariums. Put a coefficient of 3 in front of the barium on the reactant side. You now have 3 bariums on each side. You also have 2 nitrogens on each side. It is a balanced equation and you cannot reduce it. The next type of class of reaction is decomposition, but among decomposition there are 6 subtypes. I'll go over each of them. The generic form that I've given you on this particular slide says MCO3. Well, MCO3 stands for metallic carbonate when heated. When a metallic carbonate is heated, it will form a metallic oxide and carbon dioxide. So we can pick any metal to take the place of M. Any metal will take the place of M. There is no element M. Don't even give me that. There is no element M. That's standing for metal. So my reaction that I'm going to give you is rubidium carbonate is heated. That is all that I will give you. You come up with your formula for rubidium carbonate. Rb has a charge of 1 positive. CO3 has a charge of 2 negative. Do your crisscrossing. You have Rb2, CO3. Yields, when heated, put the triangle over the yield sign. A metallic oxide, in this case, rubidium oxide, whose formula is Rb2O. And carbon dioxide, whose formula is always CO2. Check to see if it is balanced. Remember, focus upon non-hydrogen, non-oxygen elements first. Are the rubidiums balanced? Indeed they are. Are the carbons? Indeed they are. Are the oxygens? Wow, indeed they are. So, bravo, that one has coefficients of 1 all the way across and can obviously not be reduced. A second type of decomposition reaction is the decomposition of a metallic chlorate. When a metallic chlorate is heated, it will decompose to yield a metallic chloride and oxygen gas. Again, the M stands for metal. There is no element M. I am going to pick aluminum chlorate is heated. That is all that I would give you. You need to come up with your formula for aluminum chlorate. The formula for aluminum chlorate is Al, parentheses, ClO3, parentheses, 3. Yields with a triangle over it to indicate it was heated. In this case, it will form aluminum chloride and oxygen gas. Aluminum chloride's formula is AlCl3, and oxygen gas's formula is O2. Now check to see if it's balanced. Again, focus upon the non-hydrogen, non-oxygen elements first. Are the aluminums balanced? Well, yes, they certainly are. Are the chlorines? They kind of are. Yeah, it kind of looks like they are. You got 3 on the left, 3 on the right. Well, gee, that leaves us the oxygens. And whoa, doesn't that really screw things up? You have 9 oxygens on the left side. Well, that's a no-no. Remember that odd-even thing? Put a 2 in front of the reactant, aluminum chlorate. When you do so, that changes your aluminums, your chlorines, and your oxygens. So now put a 2 in front of AlCl3 on the right side. And G, you've got 18 oxygens on the left side. You need to put a 9 in front of O2 on the right side. Can you reduce 2, 2, and 9? No, you cannot. So that's your balanced equation. Alrighty, the next type of decomposition reaction that I've given you is the decomposition of a metallic hydroxide. When a metallic hydroxide is heated, it will form a metallic oxide and water. Usually in the form of steam, by the way. I'm not going to be a stickler on phases. So my reaction of choice is potassium hydroxide is heated. When potassium hydroxide is heated, we know we write KOH, yields with the triangle over it. Potassium oxide, which is K2O, and H2O. Is it balanced? Non-hydrogen, non-oxygen elements first, so focus upon the potassium. No, it's not balanced. Put a 2 in front of KOH. When you do that, you change your number of oxygens and hydrogens as well. But lo and behold, it fixed everything. So 2, 1, 1. You cannot reduce. The next type of decomposition reaction is the decomposition of a metallic oxide. And there are very few metallic oxides that you have to worry about. I'm only going to ask you to worry about 2 of them, and I've specifically given you their decomposition reactions on this slide. You have the decomposition of mercurous oxide and the decomposition, of mercuric oxide, misspoke there, of mercuric oxide that yields mercury metal and oxygen gas. It is not balanced. You do need to balance it. And the decomposition of plumbic oxide, which yields plumbous oxide and oxygen gas. Again, not balanced. When you balance them, you should have, respectively, from left to right, 2, 2, 1 and 2, 2, 1. You cannot reduce. The next type of decomposition is electrolysis. And in an electrolysis reaction, you use electricity to break up what the reactant is. And if you've not noticed, I've failed to mention at the beginning, all of these decomposition reactions start with one substance and end up with more than one substance. So in this case, we're starting with one substance, we pass a current through it, and it breaks apart into more than one substance. So the 2 reactions of interest here are the decomposition of sodium chloride and of water by electrolysis. If we pass a current through sodium chloride, we can get sodium metal and chlorine gas out of it. Not exactly a great combination. Sodium metal is a pretty volatile substance, and chlorine gas is poisonous, so don't want to be around that one too much. And if I electrolyze or pass a current through water, I can get hydrogen gas and oxygen gas. Again, those are pretty exciting when, I don't know, you have some heat involved or a little spark here and there. You can get some excitement going. So they are not balanced either. I do want you to balance them. And looking at them, you will put it respectively from left to right, 2, 2, 1. And then 2, 2, 1. Pretty interesting how all 4 of these last ones balance in that manner. And then the last type of decomposition reaction is the decomposition of a weak acid, typically is what we're looking at. Not necessarily always weak, and I do wishy-washy stuff on this one. I tell you that a weak acid's formula is HA. That is indeed the generic formula for a weak acid. And I tell you that it produces water, and A, well, that's a little misleading. A is just telling you it's the stuff that's left over when you subtract out H2O, because I'm not going to make these hard. I'm going to pick acids that decompose to yield water and whatever remains once you subtract 2 H's and an O from the reactant. So let's take as an example, sulfurous acid is heated, is all that I would give you. Sulfurous acid is H2SO3. It's heated. G, I get H2O out of it, and once I subtract 2 H's and an O from H2SO3, I get SO2. Is it balanced? Go back and forth a couple of times. Sure enough, it's balanced. 1's all the way across. That brings us to single replacement reactions. At this point, you should pull out the activity series of metals and activity series of nonmetals that you had been handed at the beginning of this lesson. This activity series of metals shows us what metals are more active. Those that are in the upper section are active enough to replace hydrogen in water. Those that are above hydrogen are active enough to replace hydrogen in an acid. Those that are above each other can replace those that are below them. And if you look at the very bottom, I also have the activity series of nonmetals, the halogens in particular. And you learned that fluorine can replace chlorine, which can replace bromine, which can replace iodine, but poor little iodine can't replace anyone in a compound. The gist of a single replacement reaction is that one element or substance, can be a molecule, a diatomic molecule, wants to take the place of another element in a compound. What elements strive for is being a part of a compound. So I've given you AX plus B yields BX plus A, where you have a metal trying to replace a cation in a compound. We're going to go over three subtypes of those. The first example I'm going to give you is that lithium metal is placed in water. You always have to consult an activity series to be able to do single replacement reactions. So you first identify it as a single replacement reaction. You then look on the activity series. Is lithium active enough to replace the hydrogen in water? Indeed it is. It is in that upper section of very active metals. It helps at this point to write water as HOH, knowing that the hydrogen that will be replaced is the hydrogen that is the cation, whereas the second hydrogen is part of the anion hydroxide ion. Another name for water can be hydrogen hydroxide. Yeah, it's kind of funny, huh? So I'm going to tell you that lithium is placed in water. You're going to write Li plus H2O, or if you think it's easier, write HOH. You will predict that the reaction will work and that lithium will take the place of hydrogen as a cation in water and make lithium hydroxide, and kicks out hydrogen. Well, you know hydrogen cannot exist on its own. It has to exist as H2, so it kicks out H2. Now, it does not matter if there is an H2 on the left side. Remember that. It's that hydrogen cannot exist on its own on the product side. Is this one balanced? Well, the lithiums are balanced. Gee, that brings us to the hydrogens and oxygens, and you know what? The hydrogens and oxygens are not balanced. So I'm going to put a 2 in front of H2O to start working on my hydrogens. I'm then going to put a 2 in front of LiOH on the product side. When I do that, I've messed up the Li, so I've got to put a 2 in front of Li. My coefficients are 2, 2, 2, and 1. I cannot reduce. The next type of reaction that I mentioned was when a metal that is above hydrogen replaces it in an acid. So I give as an example, magnesium metal is placed in phosphoric acid. When magnesium metal is placed in phosphoric acid, we need to consult the activity series. Indeed, magnesium is above hydrogen. It can replace hydrogen in an acid. So Mg plus H3PO4 will yield Mg3 parentheses PO4 2. And G kicks out hydrogen. How's that hydrogen going to exist? You got it, as H2. Even though it was H3PO4 on the left side, it still exists on the right side as H2. Is this one balanced? Oh, of course not. So you have 3 magnesiums on the right side. You need to have 3 magnesiums on the left side. You have 2 phosphate ions. I'll look at those collectively because they didn't break apart. On the right side, I need to have 2 of those on the left side. I put a 2 in front of H3PO4. Gee, that fixed my hydrogens so that I have 6 on the left side. I need to put a 3 in front of H2. So my coefficients are 3, 2, 1, 3. Nope, I don't have to reduce. And then the next type that I mentioned was when a more active metal replaces a less active metal. So when that occurs, you simply have to make sure that the metal trying to kick the other metal out of the compound is above it in the activity series. So I'll give you as an example, aluminum is placed in a solution of cupric chloride. Now I write Al plus Cu, Cl2. Look at my activity series. Can aluminum kick copper out? Yeah, betcha it can. So I get AlCl3 and Cu. Is that one balanced? Nope, sure isn't. As I look at that, gee, my chlorines are all messed up, so I'm going to put a 3 in front of CuCl2, a 2 in front of AlCl3. That means I put a 2 in front of Al and a 3 in front of Cu. Alrighty. Now, let me give you just for kicks, copper is placed in water. You think that that's going to be a single replacement reaction. Indeed it could, if copper or active enough to replace hydrogen in water. Look at your activity series. Copper is way down there, even below hydrogen. It can't replace hydrogen in water. It can't replace hydrogen in an acid. Poor little copper just likes to exist in its metallic form. It'll form an oxide, that green junk that you see like on the Statue of Liberty, but gee, it can't do anything in water. So you'd write Cu plus H2O yields, and you'd write no reaction. And then the last type of single replacement reaction is when a more active halogen replaces a less active halogen. So I'll give you as an example, chlorine gas is pumped through a solution of sodium iodide. So Cl2 plus NaI. Will it work? You bet it will. Look on your activity series, or just look at a periodic table because it's in the same order as the halogens are on the periodic table. Chlorine is higher than iodine. It can kick it out of a compound. I get as my products NaCl and I2. Are they balanced? Nope, they sure aren't, so I kind of need to fix the I's on the left by putting a 2 in front of NaI, and the Cl's on the right by putting a 2 in front of NaCl, and lo and behold, that fixed my Na's as well. Okie dokie, so we only have 2 more types. The next type is called double replacement. As you see on the generic form there, AX plus BY yields AY plus BX. We have essentially cations that are switching places is the easy way to look at it, or anions that are switching places. Either way, I don't care how you look at it, just do one or the other. On the little generic form that I put there, I made my anion switch places. It doesn't matter. So, I'm going to give you cobalt 3 nitrate is reacted with tin 2 fluoride. You do not consult an activity series for double replacement reactions. You only consult an activity series for single replacement reactions. So there's no question this reaction will work. You end up getting tin 2 nitrate and cobalt 3 fluoride, which are your formulas all the way across are CO parentheses NO3 3 plus SnF2 yields SN parentheses NO3 parentheses 2 plus COF3. Is it balanced? Of course not. So take a look at, say, your tins. Gee, they look balanced. Looks good. How about your cobalts? Yeah, they look good. Your nitrates? On the left you have 3, on the right you have 2. Fix that by putting a 2 in front of CONO3 3. Fix it on the right side by putting a 3 in front of SnNO3 2. And gee, you just messed up your cobalts and your tins, so go ahead and put a 3 in front of SnF2 and a 2 in front of COF3. Alrighty, that brings us to the last type of reaction, that is called the combustion of a hydrocarbon. I can give you any variety of hydrocarbon here. So it can be a simple thing like methane, which is CH4, complex thing like paraffin wax, which is what candles are made out of, which have 20 or so carbons in them. I'm going to give you as an example that acetylene, which is called ethine. And the gist of this is you take a hydrocarbon, when it combusts, you know that it has to react with oxygen. Anytime anything burns, it has to have oxygen. In the presence of heat, it yields, in a complete combustion, carbon dioxide gas and steam. Those are always your 2 products. You always have a reactant of oxygen. The only variable here is what the hydrocarbon is. So that's why I've given you in the generic formula C sub X H sub Y. So let's take the example of acetylene, which is C2H2, is completely combusted. Okay, if that's all I give you, then you write C2H2 plus O2 yields CO2 plus H2O. If you recall, when I taught this balancing stuff to you before, I told you that the trick when you're dealing with hydrocarbons is to put a 2 in front of the hydrocarbon. It makes your balancing much easier. So let's slip a 2 in front of C2H2. Alright, when we do that, we have 4 carbons on the left. Let's put a 4 in front of CO2. Carbons are happy. Now let's go to the hydrogens. I have 4 hydrogens on the left. I have 2 on the right. Let's put a 2 in front of H2O. When I do that, my hydrogens are happy. Let's focus upon the oxygens. Look at how many oxygens you have on the left. You have 2. On the right, you have 8 in carbon dioxide because you have 4 moles of it, and you have 2 in the H2O because you have 2 moles of it, and 8 plus 2 is 10. That means I need a 5 in front of O2. Can I reduce 2, 5, 4, and 2? No, I cannot. And yes, there will be some that you can reduce. I promise you that will happen. Alrighty, that's about it. This one's a nice short one. Mr. Mooch the kitty cat is sitting above the iMac looking down, wondering why I'm talking to it. So, nice 20-minute, I can't speak anymore. You know what I'm going after. I hope y'all have fun with it. Bye.